Okay, good afternoon. So let me remind you where we were last time.
You were talking about BC dimensionality?
Right.
Oh, sorry, I thought you were asking.
Yeah, I was saying let me remind you, not let you remind me, but that's okay. So we were talking about the VC dimension. We defined the VC dimension. So to define the VC dimension, we started with the notion of shattering. So we had the definition of a class H shatters a set A. And from this notion, we defined the VC dimension of H. And the VC dimension of H is the maximum of a size of a set A such that H shatters A. If such a maximum exists, and if it does not exist, then it's infinity if arbitrarily large A's are shattered. And we saw, and this is going to be a central definition, the definition of the VC dimension. And we saw some examples of the VC dimension of some simple classes. So we saw that the VC dimension of H thresholds was 1, and the VC dimension of H intervals was 2, and the VC dimension of the class of H rectangles, and I'll put a superscript 2 here to denote that we are talking about rectangles in R2. And rectangles in R2, we saw that the VC dimension was 4. And the last example that we saw was that the VC dimension of H finite over some infinite domain, over any infinite domain is infinity. So these were the examples that we saw so far. And on top of the examples, and again, you will see more examples in the assignment. I promised you to have the assignment yesterday. I did not finish it yesterday, so I promise again that it will be ready tonight. No, it's not a joke. It's serious. So I showed you one inequality regarding the VC dimension, and that was that for every class H, the size of H is always at least 2 to the VC dimension of H. So if I want to have a big VC dimension, I need a large H. That's what it says. And the reason is that if I have a big VC dimension, it means that I have a big set A which is shattered. But to shatter a set A, I need 2 to the size of A many hypotheses to cut all subsets of A. So if I want to shatter a set of size D, I need to have at least 2 to the D many hypotheses in H. Now we can ask, is this tight? Can it be that H is much bigger than this? What do you think? And what is he thinks that it is, and I agree. Do you have an example?
Well, I mean, and so H threshold.
Yeah, like look at H thresholds. What is the size of H thresholds? We look at all thresholds on the real line. What is the size of H? The size of S is infinity. The visit dimension is only 1. And infinity is more than 2 to the power 1. So clearly, this inequality is not tight. Now, there are many other properties of visit dimension. I will list some of them, but I will leave, I think, the proof to the assignment. So one thing which is clear, so some further properties of the VC dimension. One pretty obvious one is that it is monotone in H. So if H1 is a subset of H2, then the VC dimension of H1 is less or equal than the VC dimension of H2. Because if this set can shatter anything, clearly this set can shatter it as well. And this inequality, I mean, it could be that we have strict increase here, but not a strict increase here. I just wonder if there's any other important properties that I want to mention at this time. Okay, so the next important property is we want to start relating VC dimension to learning. And now the claim that I have is that so here we have a first interesting lemma, non-trivial one. If H has infinite VC dimension, then H is not PAC learnable. So the VC dimension, we begin to see a relationship between the VC dimension and learnability. And note that if we look at our different notions of learnability, if it's not PAC learnable, then it's clearly not agnostic PAC learnable, and clearly ERM will not learn it. So all the notions we've been playing with, this is the weakest one, and this one already fails if the class has infinite VC dimension. Now, how do we prove it? I claim that basically you have already seen the proof. And the proof is that it follows from the no free lunch theorem. So, yes?
Can you give a rehash of the no free lunch theorem?
Yeah, that's what I'll do now.
Cool.
Yeah. I think that next time I have to travel, I'll ask you to replace me. You can remind us what we're doing. You even can tell what you should do next. It's great. Yes.
So we didn't actually prove the no free lunch theorem in class.
You did not prove it.
He kind of skimmed over it
We ran out
in
of
light
time.
detail. We ran out of time, yeah.
I see, I see. Okay, so I'll give a sketch of a proof, although it was not in my plan for this lecture. I mean, there is, throughout the course, I'll always have this kind of dilemma or trade-off between keeping things on a clear, intuitive level or going into proofs. And I want you, on one hand, I want you all to see that there's mathematical proofs to anything and learn how to do mathematical proofs. On the other hand, I'm well aware that when you go into a mathematical proof, some of you, many of you kind of lose the thread of thought along the way, and it may obstruct the intuition. So I'm trying to find some kind of a balance. Okay, I'll repeat. I'll give some proof idea for the no-free-lunch theorem. Okay, so let us recall what the no-free-lunch theorem is. So the no-free-lunch theorem, so this is just recall. It says the following. It's kind of a negative result about learnability, and therefore it's relevant to what we're doing here. So the no-free-lunch theorem, it says the following. Let pick any domain set X and let H be the class of all, that's important, functions from X to 0, 1. So we look at the class of all possible functions. And we want to show that it's very difficult to learn, or impossible in some sense, to learn the class of all possible functions. Okay, so in what sense is it difficult? We look at the class of all possible functions. Then if we look at M H of, say, epsilon equal 1 over 8, delta equals 1 over 8. So let me remind you what this means. It is the minimum number of examples that I need in order to guarantee accuracy 1 over 8 with confidence 7/8. I mean, the probability of failure is at most 1 over 8. The precision is at 1 over 8 or better. I want to ask how many examples do I need to guarantee such success with any algorithm. And the claim is that this thing should be at least the size of X over 2. Or in other words, no algorithm can succeed in PAC learning H for epsilon equals 1 over 8, delta equals 1 over 8, using less than X over 2 sample size. So before we even go to the proof, just note that in some sense I view it as saying we cannot learn the class of all functions. I only tell you here that you need X over 2 many examples. But in some sense, this is the difference between learning and memorization. In learning, we want that from a relatively small sample, I can deduce the behavior over the full set. And what this is saying is that if I want to predict the behavior of the full set, I basically need to see almost everything. Of course, if I see all the elements of X and we are talking about pack learning, where the labeling is deterministic, if you see every element as an example, you don't need any learning. You can just have a lookup table, memorize everything, and you know how to predict. So learning is in this gap between how many examples do I need and seeing everything. Seeing everything, I call it just memorization. And now what we're saying here, if H is the class of all functions over the domain X, then you cannot do much better than memorization. If you want to achieve some reasonable accuracy, you need to see at least half the points. So you almost just memorize. OK? Does that make sense? Does it look similar to the theorem that Hassan was stating? Yes?
So the size of X can be either finite or infinite.
Right. So for infinite X, I mean, this is stated for a finite X. For infinite X, it will mean that in order to guarantee this kind of precision, you will need infinite sample size. Right. And that's why we have this statement here. If H here has an infinite VC dimension, it will be very close to this. Then you cannot learn it. You will need infinite sample size. OK? So now let me give you any more questions about the no free lunch theorem? Yes?
What's the significance of the 1 over 8?
Oh, the 1 over 8 is just saying, you will see in a minute, it's not any magic number. It just follows from the fact that our algorithm, if it sees less than x over too many examples, will have, on expectation, its error will be quarter. And if you have error quarter as on expectation, you can show that you cannot achieve parameters better than 1 over 8, 1 over 8. It will have a quarter expectation of error. OK? More questions about this theorem? So now what about the proof? The proof is also not so mystical, and I think that I'll start with a sketch that probably look like what Hassan did, and then I'll give a more precise formulation. So proof, let's start with proof idea. So here is my set X. And we want to show that if any algorithm that you pick, if this algorithm sees less than half of the point of X, because if it sees a sample of size at most X over 2, then it sees at most half of the point of X. No matter which algorithm I have, I cannot have a guarantee that this algorithm will always be able to predict with better precision than that. So the idea is that look at the sample points that was the input to my algorithm. And let's just draw it like this. So these are the points hit by the training sample. And we know that the points hit by the training sample are at most half of the size of X. So what I have here is at least half on this side. Now, the algorithm sees these points with some labels, and it should, as a result, predict how my function is going to behave here. Now what I want to estimate, so we want to estimate, to upper bound, to lower bound, the probability that any given learner A will err on a random point. Right? That's what A has to guarantee. That will be what A has to achieve is it's an algorithm that no matter what the probability, it will not err on a random point. So if I pick a random point, if I look at all the points here in uniform distribution, and I pick a random point, what is the probability that the point will fall on the area that is not covered by the sample? So if I pick a random point, then the probability that a random test point x is not covered by S is at least half. Since S was small, S covered only half of the points. If I pick a random point in uniform, the probability it will hit a point not covered by S is at least half. But what happens if a point is here? I fix my learning algorithm. My learning algorithm have seen a sample here. The sample here was labeled in some way, and based on this, my algorithm predicts the behavior everywhere. But if there is a point here that I haven't seen, and the class H contains of all possible functions, then there are many functions. So say A predicts some label for this point. But half of the functions that agree with the sample will give this point label 0. And half of the functions that agree with the sample will give this point label 1. Since I have all possible functions, if I look at all possible functions and I fix their behavior on the training sample, still for every new point, half of them will predict 0, will say 0, and half of them will say 1. But my algorithm had to output a hypothesis. He had to commit himself to some value. So if I take kind of a random point and a random labeling rule, with probability half, my point will be in the uncovered side. And with probability half over all labeling rules, the prediction that I picked is going to be wrong. So in probability, I'm going to make error quarter of the time. And this translates into this 1 over 8 epsilon delta. That's the idea of the proof. We need to be a little bit more precise. Yes?
For the sketch of the proof, is that diagram under the assumption that our sample size is at least size x over 2?
At most.
At most.
Did I say at least?
Less than x over 2.
Oh, okay, yeah, no.
Less than.
Right, and that's the concept we're showing over in the.
If the sample size is less than half the size of x, then I know that the uncovered set is at least half. Yes?
You are assuming a uniform distribution over the sample, right? What if you have the case where like 75 or whatever percentage of the time your sample is 0.1?
Okay, that's a very good question. She argues that in order to show the failure of my algorithm, I assume that there is a uniform probability of picking every point in the sample. What happens if my probability is such that 75% of the time it picks just this point? Then I'll see my sample, I'll see this point, I'll know it's a label. Then I get my test. My test is also very much likely to be this point. So why is this argument not a defeat to my no-free lunch theorem? Yes?
M should work for any possible distribution.
Exactly. So you have to recall the definition of PAC learning. We say that PAC learning, H is PAC learnable if this MH means that this number will suffice for any distribution, not only favorable distributions. So if it needs to suffice for any distribution, it should also suffice for the uniform. So the meaning of this number is this is the sample size that is guaranteed to work, regardless of what the distribution is. So to defeat it, it's enough that I show you one distribution for which it doesn't work. Any other questions? Okay, now there is kind of a bothersome gap between the story I told you here and a proof. And the bothersome gap is that I was taking here, in order to show you that on this new point, my algorithm, no matter what my algorithm does, it will err half of the time. I needed to take probability distribution of all possible functions. But I'm learning against one's function. I mean, there is a labeling function. I get my sample, and I need to learn this labeling function. In my argument, I took an average over all possible functions. Say half of the functions will give it label 1, half of the functions will give it label 0. Therefore, my algorithm, whatever it commits to, will fail half of the time. What is half of the time? Half of the time is for half of the functions. But I want to succeed for just one labeling function. So there is some kind of looseness in my argument here. I mean, that's the basic idea, but we have to make it a little bit more precise, and that's the crucial point. That's the tedious point here. So let me give a slightly more elaborate argument here. And the trick is, you can also read the proof in the book. The proof in the book is completely precise, but it's not something that you would like to read before you go to sleep, unless for entertainment. I mean, unless you really want to fall asleep immediately. So let me give a graphical explanation of what the proof does. So we can draw a table. And in this table, what I'll have here are all possible samples of size half of x. So here I'll have S1, S2, S3, all possible samples of size half of x. And I'll have those samples with all possible labels. So this is going to be a very long list. All possible samples. I'm just looking at, so S1, why am I stuttering here? Because for us, a sample was a sequence of points with labels. But I don't want to mention the labels right now. So it's just the points. So when I say here S1, S2, it's all possible domains of the samples, just the x points of the sample without their labels. That's what I have here. And what I will have here are all the possible functions from x to 0, 1, all the possible labeling functions. So here I'll have f1, f2, f3, all possible labeling functions. OK? So it's a very big table. All possible labelings, all possible f that goes from x to 0, 1. And now, so it's a very big table. This is all possible m tuples of points, m over 2 tuples of points. And now I want to tell you what to write in an entry of this matrix. So in an entry of this matrix, what I want to write is, what I have here is I have here some labeling function, and I have here some sample. So we want to show that every learner is going to fail. So we fix a learner A. And what I'm going to write here is the loss with respect to the uniform distribution and the function fi when I get as training the sample sj. So this is I here, and this is j here. Again, the loss, or the error, of my algorithm is of A of sj. A of Sj. Okay. So if I want to tell you what is the loss, I have to tell you how am I generating points and labels. So I'm generating points uniformly over x and labeling them according to the function fi. So this is my data distribution for which I can define how well I succeed. And now I look at the prediction of my algorithm. So I say my algorithm takes as input this sample Sj. The sample Sj is labeled according to this distribution, to this fi. The algorithm outputs some function, and I will write here the error of this function. So does it make sense? I take a big table, all possible functions, all possible m tuple of points, and now I take my algorithm, feed it this m tuple of points, Sj, and I assume that the data is labeling by fi, and I check what will be the expected error of my algorithm. Any questions about how I build my table? Yes?
Is S one single point or a set of points?
S is a sample. So it is a sequence of points of size at most x over 2. At most half the size of x. Okay? So this is a sample which is the input to my algorithm, to my learner. Yes?
And don't you want to include the labels since it's an input to your learner?
Yeah, so now it includes the labels. Here it is without labels, but now I'm using the labeling fi. So I'm using the labeling fi to label the sample and to estimate my error. So I have this very big table, and now let us look at this table. So you tell me, these numbers in the entries of the tables, what kind of numbers are they? So just to estimate the size of the table. The size of the table here is x, choose at most x over 2. It's very big. It's roughly 2 to the x. The size here is all possible functions from x to 0, 1. So how many such functions do I have? 2 to the x. So it's a very big table. And in every entry of this table, I have a real number, which is the error of my algorithm when I'm using this function and this sample. So here I have 0.5, and here I have 0.3, and here I have 0.1, and here maybe I have 0. Yes?
Is x countable?
X is finite here.
Oh, okay.
We take a finite set x, and we argue that we need at least half the size for training. I mean, we argue what happens if you have less than half the points of x for training. Okay? So now I look at this table. Now, what I want to check, my next claim, is that for every column of this table, the average number, the average of all the numbers of this column is at least how much? The average number of this column is at least a quarter. Why is the average number of this column at least a quarter? Because in order to, what is a column? A column is a fixed sum m points here. So I can group together all the functions that behave the same on this set. I can group functions according to how do they behave on this sample. So there'll be sample functions that give this sample 1, 1, 1, 1, 1. There'll be functions that give this sample 0, 0, 0, 0. There'll be functions that give it 0, 1, 0, 1, 0, 1, 0, 1. I will just reorder the functions such that in every block I have functions that all agree on what they say on this sample. Now, if all those functions, if I look at a group of functions that agree on the sample, then my algorithm on such functions, when it sees the sample with labels, it gets the same input. Over each such block, all of the functions in the block behave similarly on the sample. So therefore, for all of the functions in my block, my algorithm gets the same input. It gets the sample with the labeling of the sample according to my function. So for all of the functions in such a block, my algorithm gets the same input, so my algorithm predicts the same function, A of the input that it got. But here I have all the possible functions on S, and I ask what is the probability that I'll make an error, that this will err. So now what I'm saying is that when I look at all the functions that agree on S, outside S, on any test point, half of them will say 0 and half of them will say 1. So in every such point, in every such block, I can apply this argument. In every such block, all the functions give me the same labeling for S. With probability half, a test point will be outside this S. And half of the functions here will agree with my prediction A of S, and half of the function here will disagree. When they agree, I get error 0. When they disagree, I get error 1. This will happen half the time. So the average of every such block is going to be at least a quarter. That's the argument we had here. For every such block, they all agree on the sample S. So A of S is fixed. A of S is fixed. With probability half, I see a new point. If I see a new point, half of them will agree with A of S, and half of them will disagree with A of S. Therefore, for every such block, the average of this error is at least a quarter. So if this happens on every block, then I can conclude that for all of the column, the average number that I have here is at least 1 over 4. So for every column, the average number is at least 1 over 4. So what can I say about the average number over all the matrix? I have a matrix of numbers. On every column, the average is at least 1 over 4. What can I say about the total average? Yes?
I had a question, but
Okay.
total average is probably also at least 1.
Right, but what was the question?
Is the algorithm necessarily deterministic? So
Yeah, we are talking about deterministic algorithm. We're talking about deterministic algorithms, and we will see that in the assignment that we do not get an advantage by considering randomized algorithms. Yeah. Any other questions? So there were two difficult stages here. One is understanding what do I have in this matrix. And the other one is the argument that when I fix some column of the matrix and I reorder the functions such that all the functions that agree on this domain will be together in the block. And now inside this block, they all agree on the domain, and I have a probability of error on average quarter. This happens on every block. Therefore, each column can give me an error of at least a quarter. So the conclusion is that all of the matrix has error at least a quarter. If I take the average of all the entries, if I have a matrix such that every column has average at least quarter, then of course the average of all the matrix will be at least quarter. Are some of you still with me? Yes, good. Now, if the average of all the matrix is at least a quarter, there must be a row with average at least a quarter. If the average of all the matrix is at least a quarter, there must be a row whose average is at least a quarter. Because if each row was less than a quarter, the whole matrix will be less than a quarter. So we kind of switched from saying the average of every column is at least a quarter to concluding that there exists a row with average at least a quarter. Because if all the rows were less than a quarter, I could sum over all the metrics and get less than a quarter. And I know that over all the metrics I have more. So there is a row with average at least a quarter. So I found some row that has average at least a quarter. But what does it mean? What is a row in my matrix? A row in my matrix is some labeling function fi. And what do these numbers mean? This average means. This average means that the average of all sample, all possible samples that of the error that my algorithm will make on fi, the average error is at least a quarter. So there exists a function that deceives my algorithm. I fixed my algorithm, and I found a function that forces it to make a lot of errors. Okay? It forces it to make at least quarter of errors on expectation. This means that I didn't achieve in a good enough learning. With so many examples, I could not guarantee that my algorithm, no matter what input I give it, will not make a big error. Now, how we get from average quarter to epsilon equals 8, 1 over 8, delta equal 1 over 8 will be in your assignment. That's not the crucial point here. The crucial point here is understanding this argument that if I allow all possible functions, my algorithm cannot have guaranteed success. Because if I allow all possible functions, even when I just look at functions that do the same thing over the input that my algorithm saw, half of them will say 1 and half of them will say 0 on the rest of the points. And you will see a point in the rest with probability half. So if I allow all possible functions, even if you see half the points, you cannot do very well on predicting what will happen next. OK, so this is as far as I will go with the proof of the no free lunch theorem. Are there any questions about what we did here? Yes?
Is each Sj of size x over 2?
OK, the question was, is each Sj of size x over 2? Sj will be of size at most x over 2. Because what Sj is trying to reflect is the points that fell in my sample. So I did all the samplings were of size m over 2, x over 2. But if I sample one point and then another point and then another point, there may be repetitions. If there are repetitions, then I saw samples of smaller size. You see?
I guess the question I'm asking is, like, are you taking the same number of samples for each of Sj's, or are you taking
OK. The sampling is all the time m over 2 points, x over 2 points. But this set Sj is how many points did the sample hit. You can sample 5 points, but there will be repetitions, so you have only 3 hits. So these are all sets of size at most m over x over 2. OK? Yes?
Isn't it possible that the sum of that row is extremely close to 1, and then all the rest rows are like very close to 0? And then if that's the case, then the chance of making a mistake is still less than 1 over 8.
OK. So he's asking, what did we conclude? We saw that every column will have average at least a quarter. So the average of the whole matrix is at least a quarter. So we know that there must be a row that has average at least a quarter. Now you're asking, what happens if I have one row which is really bad. It has average error 1. And all the other rows have average error 0. And I'm very happy if I'm in either of the other rows. That's what you ask? Yeah. We have to go back to the definition of learning. The definition of learning says this number should suffice for success against any labeling of the functions. So if m h is some number, it should suffice for every function, including for this bad function. The learning is a guarantee that no matter what data you see, you will not make too much error. So if I show you one configuration in which you fail, this is not a sample size guarantee for you. Okay? It's a matter of the definition of learnability. It's a worst case definition. It's a guarantee. It makes it easier to get lower bounds, to get negative results, but it makes our positive results more meaningful. Any other questions? Okay, so we have the no-free lunch theorem. Now, let's go back. Okay, so that's the theorem. What I'm saying is that a corollary of this theorem, and that's where we started, we had this lemma that says if H has infinite VC dimension, then H is not learnable. That's what we wanted to prove. Now, in order to connect it to the no-free lunch theorem, the no-free lunch theorem talked about the class of all functions over some x. And here we don't talk about all functions. We just talk about a fixed h, and all we know about it is its VC dimension. But those things are related. How are they related? So assume by way of contradiction, assume by way of contradiction that such h is learnable, PAC learnable. Then we have this function, then for some function m, you remember just a repeated definition, m goes from 0, 1 times 0, 1 to the natural numbers, mh for some such function. We have a guarantee that for every distribution P, or did I call it P or D in our definition? Not that it should confuse you, but in case it does, I want to repeat the same letter. So when we defined PAC, did I use P or D? If you just promise me that you will not be confused by the change of letter, then we don't have to stop here. So for every distribution P over my domain X, and every F in H, and every epsilon greater than 0, delta greater than 0, PAC learnable. What did I forget? Then for some H and some learner A, for every such, we know that the loss or the probability over samples going according to my P to the M and labeled by F, the probability that the loss with respect to this function of whatever A will do when it sees S, the probability this will be greater than epsilon is less than delta. That was our definition of PAC learnability. Yes?
Whenever size S is greater than or equal to MH?
Whenever the size is greater or equal than that, in particular, this M is MH. Right? Whenever M is greater than MH epsilon delta. So I just repeated the definition. So now we want to go towards a contradiction. We know that our class has infinite VC dimension. So if it has infinite VC dimension, consider MH of 1 over 8, 1 over 8. Since I assume by way of contradiction that the class is learnable. If it's learnable, I have my function MH. If I have my function MH, I can substitute 1 over 8, 1 over 8, and get some number. So this is some number. If it's learnable, it's some finite number. Now, since the VC dimension of H is infinite by VC dimension of H being infinite, there exists some set, say W subset of X, such that H shatters W and the size of W is greater than twice MH of 1 over 8, 1 over 8. If the VC dimension is infinite, then I'm shattering arbitrarily large sets. That's the definition of infinite VC dimension. There is no upper bound on the size of shattered sets. So in particular, you claim we had an infinite dimension H. You claim that it can be learned. If it can be learned, we have this function. If it has this function, there is the value of this function at 8. And since the VC dimension is infinite, I can pick a shattered set which is bigger. But now we have to go to the definition of shattered. If W is shattered, what is the set of function that H gives me over H? Over W. If W is shattered, what is the set of functions that H gives me over W? Yes. All functions. H induces every possible function from W to 0, 1. That was the definition of shattered. But now, if H induces every possible function, we are in the game of the no free lunch theorem. We have to be able to succeed against every possible function over W. So, but by the NFL theorem, in such a case, if we have if the class contains all the functions over W, M, the number of points that I need in order to get 1 over 8, 1 over 8, is at least W over 2. That was the no free lunch theorem. But W over 2 was greater than MH of 1 over 8, 1 over 8. That's how I picked W. I picked W, which was greater than twice this, so W over 2 is greater than this. So we got a contradiction. Again, the no free lunch theorem tells me if I pick a big enough set, I'll need lots of examples. And if the class was learnable, there was a fixed number of examples that will suffice. But if it has infinite visit dimension, I can pick a very big, arbitrarily big set with all functions allowed on this set. So it violates the claim that with so many examples, my algorithm could learn every function in my class H. So here we saw a connection between the visit dimension and the no-free-lunch theorem. The visit dimension talks about the size of sets over which we have all possible behaviors. And the no-free-lunch theorem tells us for such sets, you need to see at least half of the points. So if the visit dimension is big, you need big samples in order to learn. And if the visit dimension is infinite, no finite sample will suffice for these precision parameters. So it's not learnable. Yes?
Why is it that we can make the claim that the size of W is greater than 2 times M?
We can make the size of, the question was, how do I justify this claim? And the answer is that if I have an infinite visit dimension, the visit dimension is the maximum size of a set that I shatter. If it's infinite, then for any number that you pick, I can shatter a bigger set. So I'll pick this number, and the infinite visit dimension says there exists a bigger set that I can shatter. Because even infinite visit dimension just says there is no bound to the size of sets that I can shatter. Okay? So we proved the lemma, and it used the no-free-lunch theorem. So the no-free-lunch theorem was in some way a clue towards the definition of the visit dimension. We already see that in the negative side, visit dimension is, finite visit dimension is a necessary condition for learning. But it turns out that it's not just a necessary condition. That's the beauty of it. It's not just a necessary condition for learning. It is also a sufficient condition for learning. So now we get something that we call the fundamental theorem of statistical learning. The fundamental theorem of statistical learning. Statistical learning is what we are doing now. We are learning from random samples. And it says that for every domain X and every class H of functions from X to 0, 1, the following conditions statements are equivalent. So let me write the statements here. One is that H has the uniform convergence property, which means for every epsilon delta, I have a sample size that if I take such samples, they are guaranteed to be epsilon representative of H. Then my second condition will be H is ERM is a successful agnostic pack learner for H. And statement 3 will be H is agnostic pack learnable. And statement 4 will be ERM is a successful pack learner for H. And statement 5 will be H is pack learnable. And statement 6 will be VC dimension of H is finite. Okay, so we will go over it more slowly. But already from the sight of it, even without much thinking, it tells you that VC dimension is very crucial for learning. If I want to know if a class is learnable, pack learnable, or if it's agnostic pack learnable, or if ERM will succeed as a learner for this class, all of those questions have their answer in the simpler question, does H have a finite VC dimension or not? So somehow the VC dimension captures all the different notions of learnability that we've been discussing. Agnostic pack, the success of an ERM algorithm, either in the agnostic case or in the pack sense, and the uniform convergence property, the property that large enough samples are guaranteed to be epsilon representative. All of those properties are captured by the VC dimension. So that's why we call the fundamental theorem of statistical machine learning. This theorem, just for reference, this theorem was first proved by Vapnik and Chervonenkis. Vapnik, Chervonenkis proved it in 1971, but they did not talk about machine learning. They were statisticians. They talked about something in statistics which is completely equivalent. And they defined the VC dimension theorem. Then, in 1984, Les Valiant introduced the notions of pack learnability. And in 1989, another group of authors, which I will not write all of their names, it is B-E-H-W, another group of authors showed this theorem again in the context of pack learning. So the theorem has a statistical statement in the Russian literature. Then Valiant defined the model. Then these guys noticed that, or reproved, that the result of Vapnik and Chervonenkis actually applies to the new definition of learning. So that's as far as the history goes. Okay, now what we want to do is to prove this theorem. Once we have proved this theorem, we can say we got the basic theory about the statistical complexity of learning, and we can move on to two important directions. One is the computational complexity of learning, and the other is starting to look at actual algorithms for learning. But the basic statistical background is captured in this theorem. Yes?
I'm just curious. Let's say the VC dimension for edge is finite. Does that imply that edge is learnable?
Yeah, that's what it's saying. All of those conditions are equivalent.
Well, it's one way. I was just wondering if
No, no. The following conditions are all equivalent.
Ah, okay.
All of them are equivalent. Any other questions at this point? So I will start proving it, as is the case in many, I don't know how many examples you have seen of theorems saying the following are equivalent. We have to show that A implies B, B implies C, and get a whole cycle of implications. So let's start. 1 implies 2. How do we know that uniform convergence implies pack-learnability, agnostic pack-learnability, or even that ERM is successful? That was one of the results that I showed you in the second lecture. That if we have uniform convergence, if with high probability we get a sample which is epsilon representative, then I can do ERM. I can minimize the error over the sample. The sample is representative, so it minimizes the error over the class. This should ring a bell. This says with high probability I generate representative samples. Representative sample means that if I minimize the error over the sample, I also minimize the error over the class. So ERM is a good learner. Now, what about 2 equals 3? Yes?
Isn't that,
What?
isn't that trivial?
It's trivial, but in order to see that it's trivial, you have to recall the definitions. It reminds me of, I have a nephew that was studying maths in Jerusalem, and there they have those kind of, you have to, part of your grade is you have to present some material in front of the class. So he was presenting some material of the class, which included proofs, and there was a step there that he didn't prove, and the professor was sitting there and saying to him, but how do you prove this statement? So this guy did not get confused. His name is Tom. So the professor asked him, how do you prove it? And Tom, of course, didn't have a clue about the proof. So he just said, oh, the proof is trivial. So the professor looked at it and thought about it. And afterwards, yeah, it is indeed trivial. So he was impressed. So I'm also impressed. I mean, this is really trivial. Why is it trivial? Because learnable means there exists a successful learning algorithm. If ERM is successful, then of course there exists a successful learning algorithm. So it's really trivial. Okay, how do I go from 3 to 4? If H is agnostic pack learnable, ERM is successful learnable for pack learnable for H. I don't know how to do. Yeah.
It's a stronger statement for 2, so you can.
Right. It's a stronger statement for 2. It doesn't follow for 3, but it follows from 2. Because it's always harder to agnostically learn than to just pack learn. So if ERM agnostically learns, ERM just pack learns. So this is implied by 2. And now 4 implies 5. Because if ERM is a learner, then there is a learner. So the class is pack learnable. So we get 4 implies 5. The same way that 2 implies 3. Or if you want, you can get 3 implies 5. If it's agnostic pack learnable, then it's pack learnable. So we got 5. What about going from 5 to 6? If it's pack learnable, why should it have finite visit dimension? We just proved that if it didn't have a finite visit dimension, it would have an infinite finite visit dimension, so it will not be learnable. So this is what we just proved. So we are almost done. Why did we need 2 Russian mathematicians to prove it? What is still missing? 6 implies 1. So for 6 implies 1, we'll have to work hard, and we will not do it today. That's now our plan for the next week. That's the hard part. That's the difficult part. But for now, the importance of this here is that to show you how significant it is to understand the VC dimension. Because the VC dimension tells us that things are learnable. And what we will also see, and I don't think I will do it today, is we will see that we can have quantitative versions. I mean, because all of those uniform convergence property, PAC learning, they have to do with a function. They talk about existing of a function m of epsilon delta, which tells us how many examples are we going to need. It turns out that not only there exists such a function if we have a VC dimension, but we can estimate this function very well just from the VC dimension. So the VC dimension actually determines how many samples you will need. It not just tells you can you learn or can't you learn, but it determines how many samples you need. So we will have a stronger version of this fundamental theorem in which we will have sample sizes. And we'll see that all those sample sizes are determined pretty tightly by the VC dimension. But that's the plan for our next lecture. At this point here, rather than introducing more heavy theorems and notation, I want to go to something a little bit more practical. So what is a little bit more practical topic that I want to talk about? I want to talk about the most common learning class that's being used in practice. So in practice, here we all talk about some hypothesis class H. What is happening in practice? In practice, one of the most common, so a practical class H is the class of linear predictors. Over Rn. And this is the class that I want to talk about now. So what are linear predictors over Rn? In a picture, if we are over R2, it means that I want to take some line as a predictor and predict plus here and 1 here and 0 here. So sometimes it's also called the class of linear half spaces, because you take your space and you cut it into half. How does such a predictor look? If I have a point x and I want to, well, how does such a predictor look? So we will define a little bit more precisely this class, and then we'll explain why it is such an important class. Okay, so here is a formal definition of this class. The class H, S, N, half spaces over n dimensions. So let my x be the real space Rn, and for given some vector W in Rn, so it's a vector, and some number B in R, let H, the predictor defined by W and B. Now I want to define a function that uses these parameters and now gives a label to every point. So x of x is also a vector in Wn. It is going to be the sign of Wx plus b. Or if you don't like, this is notation of inner product. Or in other words, if W is a vector, it's W1 up to Wn, and x is also a vector, x1 up to xn, then HWB of x is going to be plus 1 if sigma I goes from 1 to n, Wi xi plus b is greater or equal 0, and minus 1 otherwise. So you see, the WB, they define a line. W gives me the direction of the line, and B gives me how much it is lifted away from the origin. And one can see that the sign of this substitute the coordinates xi in the coefficients wi. Wi is a set of coefficients, xi is a point. I substitute this point, and I get that if the product is negative, I'm below the line. If it's positive, I'm above the line. So this is a formal definition of take a line, or in more dimensions, you take a linear half space, and you predict 1 if the point x is above it, and 0 or minus 1 if the point x is below it. So formally, it's the inner product, the sign of the inner product. And if we figure out what it says, it's the sum over all coordinates of the coefficient wi times xi. And at the end, we add this b. Now, I haven't defined the class yet. So what is the class? So HSN is the class of all functions of this form, such that W is in Rn and B is in R. Because here we just defined what is a single such function. And now we are looking at the family of all such functions, and that's a class of functions. Yes?
Just a minor detail. Here we use +1, -1, but can we just think of it as 0, 1?
Right. So here I was asking about my switching between labeling 0, 1 to labeling -1, +1. Nothing that we did so far depends on the identity of the labels. It could just as well be blue and red. We just need two different labels, and everything that we do is playing with two different labels. So when we talk about linear predictors, because it's a sign function, it's more natural to talk about +1, -1, whereas before we talked about 1 and 0. But it's just the main thing is that we have two distinct labels. Yes?
If h of x is equal to 0, is it just one of those cases where you can't determine?
No, we will just arbitrarily, if it's 0, we'll arbitrarily say it's plus, and if it's below 0, we'll say it's minus. So we can also look at all the predictors that for 0 give you minus, and so it doesn't really change the discussion. And in reality, okay, so one last word, because we really have to finish. Why are those predictors so important? Because those predictors are very natural. Assume that I want to decide whether I'm going to hospitalize a patient or not. So my coordinates, I have my patient, and I have measurements of the patient. And this could be blood pressure, and this could be the heartbeat rate, and it could be the temperature of the patient, and so on. And I have to make a decision whether, a binary decision, hospitalize him or not. If I have such a predictor, there is something very natural here. It gives you a weight to each of the features. Blood pressure is that important. Temperature is that important. It tells you kind of weigh together all the considerations. This is the importance of the consideration, blood pressure. This is the importance of the consideration, temperature, and so on. You have a sequence of features, and the weights can be thought of as how significant, what's the relative significance of each feature. Okay, so we'll continue the discussion next Wednesday. Have a nice weekend.